Alright, so in this problem we are asked to consider the displacement function for an object in simple harmonic motion. That displacement function is d of t equals 4 cosine of 4 pi t. So the first thing we need to do is identify components of this simple harmonic motion and then construct a plot of that simple harmonic motion. So let's start with the amplitude here. So we know the amplitude is given to us by the absolute value of the vertical stretch factor for our function, or for example, if we were considering, say, a form d of t equals a times the cosine of omega t, we know that the absolute value of a is going to give our amplitude. Our 2 pi over omega will be our period, and omega over 2 pi will be our frequency. So looking at these ideas and how they relate to our problems here, note here that we're looking at the a being equal to the absolute value of 4, which is just equal to 4. So our amplitude here, 4. How about for our period? Our period is defined as 2 pi over omega. If we look at 2 pi over omega, we have 2 pi over 4 pi, which is just equal to 1/2. So we have that the period is equal to 1/2. For frequency, we look at the reciprocal of the period, or look at omega over 2 pi. In either case, we'll find that that period, or that frequency, excuse me, is equal to 2. What does this mean? Well, note then that this means it takes, if our, for example, time was measured in seconds, it would take 1/2 time units, or 1/2 a second, for us to complete one period or one cycle of motion, starting at, in this case, a maximum value, hitting an equilibrium value, going to a minimum value, returning to an equilibrium value, and finally to a maximum value. That would take us 1/2 time units, or 1/2 time seconds. And therefore, we would complete 2 cycles or 2 periods in 1 time unit, or 1 second. Let's go ahead and look at a plot of this function to help us further determine properties of this object in simple harmonic motion, or at least just see another way we can represent those ideas. So I'll plot a period above and a period below. So I know my period will be equal to 1/2. Actually, I'm going to plot 2 periods above, I believe, and 2 periods below. So here I have my periods incremented, and all these periods I'll increment into 4 important, if you will, evaluations. Our maximum values, which we know will be given by the positive of our amplitude, and the minimum of our values, which will be given by the negative of our amplitudes. So we can look at the little dotted line right there to help me find my minimum values. We'll put a little dotted line right here. Let's find our maximum values. We consider we have a cosine function, so we'll start at a maximum value a quarter of the way through its period. Cosine takes an equilibrium value halfway through a minimum, 3/4 the way in equilibrium, and returns to a maximum position at the end of its period. So here's 1 period of cosine, or 4 cosine of 4 pi t. By the periodicity of cosine, we should be able to construct the rest of this graph, or by the evenness of this function, we'll have symmetry over the y-axis. And so we get the graph of our d of t equals 4 cosine of 4 pi t. That would be the last part of our problem here. So again, note that here we have all of our solutions, but note this relationship between period and frequency, where here we can see we complete 1 period. See, here's maybe the start of a period, and after 1/2 time units, whatever that time unit might be, we complete a period. We started at a maximum, we go all the way down to our minimum, return to our maximum value. This is a full period, or for a cycle for motion for our object. And note that if our period is 1/2 in 1 time unit, we would complete 2 cycles. See here in 1 time unit, or from from t equals 0 to t equals 1, you can see we complete 2 cycles. Here's our first period, say, and here would our second period be. Again, where we can see we complete another cycle between 1/2 and 1.